chapter 24 was mentioned briefly in chapter 23. This is about paired data. So chapter 24, we needed 2 independent samples of data. Well, chapter 24, we're going to still be looking at 2 pieces of data, but they're not independent of each other, they're paired. First thing, this is the last chapter of part 6. This is the last chapter in part 6. So your next test actually covers parts 5 and 6. It's on all the inference we've learned so far. That's chapters 18 through 24. That's going to be proportions and means. So it's going to be on 1 proportion z-test, 2 proportion z-test, 1 proportion z-interval, 2 proportion z-interval, 1 sample t-test, 1 sample t-interval, and a 2 sample t-test, 2 sample t-interval, and a paired t-test and a paired t-interval. So that's a lot of information. Also all your errors and powers and everything else. So data are paired when the observations are collected in pairs or they're observations from one group that are naturally paired to observations in the other group. So that would be an example like if we collect data on husbands and wives and we collect data about the husbands and data about the wives, like the same data variable, that would be paired because those people are related to each other, or siblings. We might have twins or something, then we were like studying something with twins. The data value for twin 1 is paired to the data value for twin 2 because they are paired together. Paired data arise in a number of ways. Perhaps the most common is to pair subjects with themselves before and after a treatment. That's a very common type of paired data. We'll look at a scenario maybe in the practice problem somewhere about like you know how they have mice run mazes, and I think they have like a mouse run a maze and there's peanut butter at the end, and then they have the same mouse run a same maze or something like that, but there's cheese at the end. And so the idea is to see which one they go to faster. But since it's the same mouse, that would be paired data. It's not different. A sample of mice do the peanut butter and a different sample of mice do the cheese. If that was the case, it'd be independent samples. But when it's the same mouse doing it before and after, that is a type of paired data. When pairs arise from an experiment, this pairing is a type of block. That's what we call blocked design, is when you have paired data from an experiment. When they arise from an observational study, we say it's a type of matching. If you know the data are paired, you can and actually must take advantage of it. So like I was talking about with the mice, you might get that data in the peanut butter time comes in like a list, and then the cheese time comes in a list. So it looks like the last chapter where it was 2 sample t intervals or tests. But you need to know from the context of the study and from the way the data was collected that this data is actually paired. So you can't go by the way it looks. You have to go by context and how was the data collected. If it is paired, you must do a paired test. Like you can easily put this in your calculator and do a 2 independent test, but it would be incorrect. It would be wrong. So instead of 2 independent samples, we really just have 1 sample of paired data. So even this is in 2 different lines, it's really 1 sample of, if this is 10 mice, it's just the 1 mouse before and 1 mouse after. And then this mouse before, or peanut butter, and this mouse cheese. We examine the pairwise differences. We examine the pairwise differences. Sorry, I'm not 100% sure what goes in those blanks at the moment. Okay, using a paired t-interval or a paired t-test on the differences between the data. Now just be aware that there's no test in your calculator called a paired t-interval or a paired t-test. If you search through all of these, they're not there, okay? So that's going to be important that you understand how you still use your calculator. But the way we do it is we actually do it on a third list of L1 minus L2. So here we have peanut butter, say, in L1 and cheese in L2. We're going to go to L3 and we're going to tell L3 to subtract those two numbers. And we're going to make one list of the differences. So we're going to look at one list of the paired differences. And since it's only one list, we're going to ultimately end up doing just a one sample t-test or a one sample t-interval. Because it is the differences we care about, we treat them as if they were the data. The differences are the data. And we are going to ignore the original two sets of data. So once I get this third list of the differences, I can actually delete these from my calculator. I'm only interested in the one list. So mechanically, a paired t-test is just a one sample t-test for the means of the pairwise differences. The sample size is the number of pairs. We don't call it a one sample t-test, we call it a paired t-test, but mechanically in our calculator, we're just going to be doing a one sample t-test in our calculator. The assumptions and the conditions, you need to make sure the data is paired. So you need to state that. You need to check that and state that the data must be paired. Independence assumption, you don't have two groups anymore, so you don't need to do this for two groups. You just need to state that the data must be independent of each other. That means like mouse 1 needs to be independent of, say, mouse 2. That does not mean that this list is independent to that list, because it's not. This first mouse is paired in the two lists, but I need this mouse to not be related to this mouse, not be related to that mouse. I need the individuals in each list to not be related. Excuse me. Randomness can arise in many ways. What we want to know usually focuses our attention on where the randomness should be. So we need if it's an experiment, they should randomly assign the mouse to go into peanut butter first or cheese first. That's how you randomly assign them to the groups. If you're picking people from a population, we would like that to be a simple random sample. The normal population assumption, we need to assume that the population of differences follows a normal model or nearly normal model. We check this with a histogram of the differences, and you can also check a normal probability plot. Remember, normal probability plot should be linear, histogram should be roughly unimodal and symmetric. Make sure you are checking one histogram. There's only one thing to check, not two. One histogram for the differences. It's not two groups, it's one group, and you're checking the differences shape.